Hi there. In this video, we'll be discussing section 5.5, the distribution of a linear combination. Let x sub 1 through x sub n be a sequence of end random variables with PDF given by f going from Rn to R. And that really isn't just PDF, it's joint PDF. So this is a joint PDF that relates all the random variables, and it's given like so. So to recall what this is, the joint PDF when we have several random variables looks like the following. So the probability of the following event where random variable x1 takes on a value on the interval from a1 to a2 and b1 and x2 takes on a value on the interval from a2 to b2, continuing on, all the way down to x sub n takes on a value on the interval from a sub n to b sub n. So the commas are and, so if you'd like, they're intersections. Since we're making statements using inequalities, we've been using commas, but these are ands. So all these conditions must be met. So what's the probability that happens for any given particular outcome of our sample space? Well, this was, if you recall, this is the n integrations. So it's an integration in Rn that looks like the following. Okay, so we have n integrations, and it's of our PDF, joint PDF, F, with arguments x sub 1, x sub 2, all the way up to x sub n. And we rewrite this as d xn, that's the first integration. dxn minus 1 is the second, all the way up to the first one. dx1. So there's a product in here, kind of squeezed it in, but it's dot 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 dx1. So this is a product of n differentials. So for short, in this is how we've defined this joint PDF. There exists this joint PDF that relates these things as follows. It will be easier or less cumbersome to write this as the following. This is equal to the integral over the region A, which is contained in Rn, of f of x hat, or x vector sign, dx like so. So I'll explain these pieces, and many times it's already well understood what our region A is. So A is defined as this region. It's a box sitting in Rn. And so a lot of times we just drop the Rn if we understood what space it's in. So this is the integral over A. dx bar. So in this particular case, A is given as follows. So A is our rectangular region. For the first component is A1, the interval A1 to B1, cross A2 to B2, AN to BN, and this is a region that sits in Rn. We also have notationally, we'll represent x vector sign, so x arrow is denoted by the point or vector xn. So this is a point which can also be interpreted as a vector that sits in Rn. And it's a little bit confusing, but when we say dx vector sign here, so dx arrow, what we mean is not a differential change in the vector x hat, but rather a differential volume surrounding the point x hat here, or x arrow. So this is in fact equal to dx1 times dx2 up to dxn. So these are differential volumes, and this is what we mean when we set up the following integration. So it's the limit of Riemann sums over this particular region. So we can generalize this in general. When doing these sort of things, we want to talk about probabilities of events with random variable x1, x2, all the way to xn. We can define the following random vector. So random vectors have an entire area, so that's an entire theory, but for us it's just notational. It's just the random vector sitting in Rn with first component random variable x1, second component random variable x2, all the way up to the random component variable xn. So for us, I'm simply introducing this notation to make the following derivations of 5.5 less cumbersome. So the probability, so let's let A be any region in Rn. Then it follows that the probability that our random vector is an element of the region A, which can be interpreted as the probability that this n tuple, this random n tuples, an element of the region A, is simply the integral over A. So this is an n-dimensional integral again of our joint PDF, f of x vector x dx, just like as follows. And these pieces are defined as a So some important characteristics about the integral operator. So we'll just talk a little bit. So this is more of a Calc 3 sort of exploration, but it'll be helpful to kind of grasp the notation and what we're talking about. Is that let A be a region in Rn, so an integrable region, and let H and G be functions from Rn to R. So what does that mean? Is that, again, to explain this notation, which we used previously as well, it means that G takes inputs that are vectors from Rn and gives an output of a real number. So G is a scalar function, just like how our joint PDF f is a scalar function from Rn to R. Similarly, H is also a scalar function from Rn to R. So we're only considering integrals of this sort. Then one, without going into the theory of integration, the integral, n-dimensional integral of a sum of functions is the sum of n-dimensional integrals. Also, number two, for any scalar a, multiplied by our scalar function g. So we integrate this thing. This is equal to a times the integral over that region just like so. So 1 and 2 make the integral operator that takes a function and gives us back a real number. So the real number associated by integrating that function over the region A, this is a linear operator. So we know from calculus 1 that the integral in one dimension, so the one-dimensional integral, definite integral, is in fact a linear operator. So I won't go into the integration theory, but the development's the same. So these are limits of Riemann sums, and therefore, since they're limits of Riemann sums, it's not a surprise that they have this property, the properties 1 and 2. So put these together, we have the following. So the integral, definite integral over the region A of a linear combination, is the linear combination of definite integrals over the region A. So it distributes over linear combinations. The integral of a linear combination is the linear combination of integrals in Rn. So we can generalize this. So this means that this integration, the process of integration, definite integration, is a linear operation. I'm going to put this as number 4, which will be important, is that we can generalize this to the following way. We'll use k. So it doesn't. We've already used n. N is our n-dimensional. N is the space of our dimension. So this summation inside here defines a new function going from Rn into R. And it's given as follows. So the integral operator, definite integral operator, can be applied over linear combinations. So the definite integral of a linear combination is the linear combination of definite integrals. So in this sense, the integral A, which is kind of bad notation here, we can think of this as a linear operator. And again, I didn't note here, G sub I goes from Rn to R for each I. So these are scalar functions on the space of Rn. Just put a little box here so that doesn't get caught up in all the details. And this is true for each I. Okay, so with that said, we can now generalize or talk about expectation. So we've used a lot the fact that the expectation operator is a linear operator. But we've used the expectation on more than just two variables. We've had a proof that the expectation operator is linear when we have two random variables. So we assume we still have our n random variables. So let's let h go from Rn into R. And for us, we're going to assume such a function is integrable. So that's important. It has to be integrable. Then we can define the following new random variable. Y is h of the random vector x. And again, what does that mean notationally? This is h, where the first component is the random variable x1, second component is the random variable x sub 2, continuing on to the nth component is random variable x sub n. Then the expectation value of y, by definition, is the integral over R. So this can also be rewritten from negative infinity to infinity of y times f sub y of y dy. So this is just definition of expectation to help iterate that there is a PDF for the random variable y. There exists one. But for us, we don't want to go about having to compute that PDF. It turns out, which this is actually a theorem, but we are taking it as definition in this course, is that this is equivalent to the integral over the whole space Rn. So we use this is a simpler way. This is just n integrations from negative infinity to infinity. So we're integrating over the whole space Rn. Just like how the integral over R is just the integral here from negative infinity to infinity. Sometimes it's more convenient to just put the space below the integral. And so this is the same as the following. H of the vector x times our joint PDF f of the vector x dx. Now recall, f is the joint PDF of x1, x2, all the way up to xn, defined on the first page. So this is how we define expectation. It has this concrete definition, but this is equivalent to the following. So we will take this as actually our definition because this is easier to work with instead of having to compute this PDF of capital Y. And this is for any such integrable function h, so a scalar function on Rn. In particular, what we're going to be interested in is when y is defined by a linear combination. So what this means is that our function h is defined like so. It's a1 times x sub 1 all the way up to a sub n times x sub n. And so it's this linear combination of the xi's, which in short can be written using this sum. And this is called a linear combination. So we're going to end this video, this is the first of a few, at least two, with the following proposition. So we're going to need this for the rest of 5.5, is that the expectation operator is a linear operator. So we've been using this fact in section 5.4, but this gives a quick proof that it is true for n random variables. Also, we should point out that the x sub i's here, x1, x2, xn, do not form a random sample. In fact, we haven't even assumed independence of these things. They're simply a sequence of random variables that may or may not depend on one another. So this is the most general case we can take, and even in that very general setting, the expectation operator is still a linear operator. So to see a proof of that, we prove in the following way. So the expectation of our linear sum, our linear combination of the x sub i's, we want to show is the linear combination of expectations. So by definition of the expectation, this is the integral over all of Rn, so it's an n-dimensional integral of the function evaluated at the vector x. So again, that is just replacing our random variables with variables. So this is the sum just like so. Given as follows. Now this is then equal to, we've already shown that the integral operator over n dimensions is a linear operator. So therefore, well, first let's distribute the f, I suppose. So this is the integral over Rn of the following sum. Just like so. So now, using the fact that the integral operator is a linear operator, the integral of the linear combination is the linear combination of integrals. So this is now the sum just like so. By definition, each one of these terms is the expectation of x sub I. Almost wrote a sum there, so that's an E. So let's rewrite that. And this completes the proof. So this is not very surprising. The expectation is a linear operator because it's defined directly in terms of this definite integral. And because the definite integral in n dimensions is a linear operator, so is the expectation operator. In the next videos, we're going to use this fact to derive many results that generalize to covariance, variance, and other such things.